The modern world does not run on oil alone. It runs on chips. And behind every phone, server, AI model, car, satellite, and cloud platform lies a global semiconductor system so fragile, so concentrated, and so important that a few bottlenecks can affect the entire world. Semiconductors are the hidden foundation of modern technology. They power smartphones, laptops, electric vehicles, cloud servers, industrial systems, military hardware, and artificial intelligence. Without semiconductors, modern civilization does not function. But the semiconductor industry is often misunderstood. Many people imagine it as a normal manufacturing sector. A company designs a chip, a factory builds it, a product ships. The reality is much more complex. The semiconductor world is not one industry in the simple sense. It is a global system, a tightly linked chain of design, software, intellectual property, equipment, materials, fabrication, packaging, logistics, energy, and geopolitical control. And because so much of that system depends on a small number of critical players, the whole structure is far more fragile than it appears. To understand the global semiconductor system, we need to break it into layers. The first layer is design. Not every company that sells a chip manufactures that chip. In fact, many of the most important firms in the world focus primarily on design. Companies like NVIDIA, AMD, Apple, Qualcomm, and others create semiconductor architectures, GPU systems, mobile processors, and specialized computing chips. These firms define what the chip should do, its logic, its structure, its performance goals, its power profile, its market use. But a design is not yet a chip. It is a blueprint. To turn that blueprint into reality, companies use specialized design software. This is another hidden layer in the semiconductor system. Electronic design automation tools are essential. Without these software environments, modern chips cannot be designed at the complexity required by advanced computing. That means even the design layer depends on a smaller tool layer beneath it. The second major layer is manufacturing. This is where the system becomes even more concentrated. Advanced semiconductor manufacturing is one of the hardest industrial activities ever created. It requires extraordinary precision. Modern chips are built using transistor structures measured in nanometers. At that scale, even tiny imperfections matter. The facilities required to produce these chips are known as fabs. Fabrication plant. These are not ordinary factories. They are clean room environments built around extreme control. Air purity, temperature, vibration, materials handling, chemical processes, photolithography, etching, deposition, metrology. Each production step must be controlled at microscopic scale. A modern advanced fab costs tens of billions of dollars. That alone creates concentration. Only a small number of companies can build and operate such facilities. At the highest end of manufacturing, one company stands out above all others: TSMC. The Taiwan Semiconductor Manufacturing Company is one of the most important nodes in the entire global technology system. Why? Because many of the world's most important chip designers do not manufacture their own chips. They rely on foundries. And TSMC became the most important advanced foundry in the world. This means that a large part of modern technology depends on one manufacturing system operating at extraordinary precision inside a narrow geopolitical context. That is a structural vulnerability. But TSMC is not the whole system. There are also integrated manufacturers such as Intel and other foundry players such as Samsung. Still, the key point remains: the most advanced chip manufacturing capacity is concentrated. That matters because semiconductor production is not easily replaceable. If one advanced fab goes offline, the world cannot simply duplicate that capacity overnight. The next layer is manufacturing equipment. This is one of the least visible but most important parts of the semiconductor system. Chip factories do not create advanced semiconductors using generic machines. They depend on extremely specialized equipment built by a very small number of companies. Photolithography machines, deposition systems, etching tools, metrology platforms, wafer handling systems, and inspection technologies are all part of this chain. Among these, one name is especially important: ASML. The company became globally critical because of its role in advanced lithography systems, particularly extreme ultraviolet lithography. This means that even the company's manufacturing chips depend on another narrow bottleneck. The fabs need the machines, and the machines come from a limited set of suppliers. This is how the semiconductor system works. Each layer depends on another layer beneath it, and almost every important layer is concentrated. The next layer is materials. Chips are not made from ideas alone. They require ultra-pure silicon wafers, specialty gases, chemicals, photoresists, substrates, metals, packaging materials, and highly controlled industrial inputs. If these flows are disrupted, production slows down. That means the semiconductor world is not only a story of chip firms and fabs, it is also a story of industrial materials and process ecosystems. Then comes packaging and advanced integration. For many people, a chip is complete once it leaves the fab. But in reality, packaging matters enormously, especially in the AI era. Advanced processors increasingly depend on packaging methods that connect multiple dies, memory stacks, and thermal structures in extremely efficient ways. So even after the wafer process is complete, another layer of specialization continues. This creates yet another bottleneck. Then there is logistics. Semiconductors move through a global chain. Design may happen in one country. EDA tools may come from another. Manufacturing equipment from another. Wafer production in another. Packaging in another. Final integration elsewhere. End products assembled elsewhere. This means the semiconductor industry is not just global in market reach. It is global in physical dependence. And that dependence creates vulnerability. A disruption in one region can affect the whole chain. A restriction on one tool can affect global output. A delay in one manufacturing segment can spread into multiple industries. This became visible during recent global shortages. When semiconductor flow was interrupted, the consequences appeared everywhere. Cars could not ship on time. Consumer electronics slowed down. Industrial products faced delays. Cloud expansion faced pressure. Prices rose. Planning became unstable. That tells us something important. Semiconductors are not just a product category. They are a civilization support system. The global semiconductor system matters because it sits below almost everything else. Now add artificial intelligence. AI increases the importance of semiconductors dramatically. Modern AI systems depend on advanced GPUs, accelerators, memory systems, and high-bandwidth interconnects. That means the semiconductor stack is no longer only about consumer devices or office hardware. It is now directly connected to one of the most important technological races in the world. The AI race is partly a chip race, and the chip race is partly a manufacturing race. This makes the semiconductor system strategically central. Control over advanced chips increasingly means influence over compute. Influence over compute means influence over AI. Influence over AI means influence over productivity, defense, software, automation, and economic power. This is why governments care so much about semiconductors. Because the semiconductor industry is not simply commercial, it is strategic. That leads to the geopolitical layer. If the global semiconductor system is concentrated, then geopolitical tension becomes infrastructure risk. When states impose export controls, chip flow changes. When countries subsidize domestic fabs, capacity shifts. When tensions rise around manufacturing geographies, markets react. When equipment access is restricted, long-term competitiveness changes. This is one reason why the semiconductor system cannot be understood only through business. It must be understood through power. Who controls design leadership? Who controls manufacturing leadership? Who controls the tools? Who controls the materials? Who controls the geography? Who controls the choke points? These are system-level questions. And they matter because the answers are uneven. No single country controls everything. No single company controls everything. But a small number of firms and geographies control critical bottlenecks. That is the defining feature of the global semiconductor system. It is distributed, but not evenly distributed. It is global, but highly concentrated. It is resilient in some ways, but fragile in others. And because it sits beneath so much of modern life, small disruptions can create outsized consequences. This is also why semiconductor expansion is so difficult. People often say countries should simply build more fabs. But building a fab is not enough. You need skilled labor, process knowledge, equipment access, supply chain depth, material flows, energy reliability, water systems, long-term capital, technical culture, operational excellence. This is why semiconductor leadership cannot be copied quickly. It must be built over years and decades. The result is a world where a few players matter enormously. Design firms matter, foundries matter, tool makers matter, cloud companies matter, governments matter, energy systems matter. This is not a normal industry with easy substitution. It is a tightly structured technological ecosystem. So how should we really think about the global semiconductor system? Not as a market of isolated firms, but as an infrastructure network, a network with choke points, a network with concentrated leverage, a network where different actors control different layers, and where power comes not only from size, but from position inside the system. That means the most important companies are not always the ones consumers see. A consumer may know Apple or Nvidia, but the deeper system also depends on TSMC, ASML, material suppliers, advanced packaging systems, and industrial process networks. This is why the semiconductor industry is so powerful. It is mostly invisible until something goes wrong. When it works, modern civilization functions smoothly. When it breaks, everything feels the pressure. Phones, cars, cloud services, military systems, AI, infrastructure, industrial production, everything begins to slow down. That is the real lesson. The world is now built on chips, and chips are built on a global system that is more concentrated and more strategic than most people realize. The future of technology will not be shaped only by the companies designing the next product. It will also be shaped by the hidden industrial system making those products possible. And that system is the global semiconductor system. A small number of critical layers, a small number of critical players, a global dependence, and a set of bottlenecks powerful enough to shape the future of technology itself.